Today we're going to take a look at upper sums and lower sums. So an upper sum is what we use to approximate the area under a function. Let's say this is our function, and we're only looking between a and b. We've got a particular area, and we know that we can approximate that area using rectangles. So we can draw in a series of rectangles, and if we go, in this example, from the right endpoint, we end up with an over approximation. Now with an upper sum, we don't necessarily know how many rectangles we're using. In previous examples, we may have used 5 rectangles. But here we're using n rectangles. So when we find an upper sum, we're going to have a general formula for an over approximation using n rectangles. And similarly for the lower sum, if we take a look at, here's a function f of x. We just look at the area from a to b, and draw in some rectangles that under approximate the area, we can find a formula that will under approximate the area using n rectangles. So here's a specific example. We're looking for the upper sum for the region bounded by f of x equals x squared and the x-axis between 0 and 2. So we're looking at this region right there. Okay. So here's our f of x, and if we want to create an upper sum, we would draw rectangles from the right endpoint. Now if we add the areas of these rectangles, we would have an over approximation for the area. Now we need the base and the height, so let's start with the base of each rectangle. We know is delta x. And that's going to be the length of the interval, which is 2 minus 0, divided by the number of rectangles. Now we don't know how many, so we leave this in terms of n. Now for the height, we know that we're using a right endpoint, so we need to find f of the right endpoint, which would be f of delta x I plus a, and a in this case is 0. Okay, here we go. So the upper sum is the sum of the areas of n rectangles. We always start with the first rectangle, we end at the nth rectangle, and the area is the base times the height. So now we use our properties. We can take out that 2 over n. F of 2 over ni, we plug that into our function, and it becomes 4, this is an n, 4 over n squared I squared. So we can take out this 4 over n squared, and outside of sigma, we will now have 8 over n cubed. And we have a formula for the sum as I goes from 1 to n of I squared, and that's n plus 1, 2n plus 1, all over 6. We can simplify this a little, and we end up with 4. That's going to be over 3n squared. And let's distribute that numerator. Let's see, we're going to have 2n squared times 4 is 8n squared. Then our middle term will be 3n times 4, which is 12n. And our last term will be 1 times 4, which is 4, all over 3n squared. And this expression here is our upper sum. So what this means is if we decide to approximate the area using 10 rectangles, we would set n equal to 10, and that would give us our approximation. Or if we wanted to use 1,000,000 rectangles, we could substitute 1,000,000 in for n and find that over approximation. We're going to do the same thing again except for the lower sum. Okay, now the lower sum. Very similar picture. Here's our x-axis, our y-axis. We're only looking between 0 and 2. We know that f of 0 is 0, and that f of 2 is 4. And our graph curves up like this, so here's our f of x. And there's our region. Now we want the lower sum, so when we draw in our rectangles, we want to use the left endpoint so that we have an under approximation. So now we're going to find the sum for an unknown number of rectangles. So the base is delta x. This will be the same. The height will be f of the left endpoint now, which will be f of delta x times I minus 1. Okay, so our sum looks like this. We've got the sum as I goes from 1 to n of the base times the height. So this is our height. We're going to substitute our 2 over n times I minus 1 into our x squared. And that's going to become 4 over n squared times I minus 1 squared. So here we're squaring all of this. This becomes 4 over n squared, and then we also have to square I minus 1. So here we're going to have an 8 over n cubed. Let's just take that out. So we've got 8 over n cubed. And now we can distribute this I minus 1 squared. So that becomes I squared. Let's make that a little neater. Oops, okay. I squared minus 2i plus 1. And now we can use our properties of summations to split all of that up. So we're going to have this 8 over n cubed times a sum as I goes from 1 to n of I squared minus 2 times a sum as I goes from 1 to n of just I plus the sum as I goes from 1 to n of just 1. And now we substitute our formulas. So we're looking at n plus 1, 2n plus 1 over 6 minus 2 times n plus 1 over 2 plus n. Okay, I ran out of room there, so what we had was 8 over n cubed, n plus 1, 2n plus 1 over 6, minus 2n plus 1 over 2 plus n. So let's combine all of this. This is over 6. So we'll have in the numerator 2n cubed. Our middle term will be 3n squared. And then plus n minus, we need a denominator of 6, so we'll need to multiply this by 3 and this by 3. So we have 6n squared plus 6n plus 6n over 6. Okay, let's combine all of those like terms. Still have this n over cubed out here, or 8 over n cubed, I mean. So 2n cubed, we've got a 3n squared minus 6n squared is negative 3n squared. Then we've got an n minus 6n plus 6n, so that's just going to be n over 6. And now let's take out one of these n's and cancel with one of those. So we have 8 over n squared, 2n squared minus 3n plus 1 over 6. We can simplify the 8 and the 6. And again, you can do your algebra in any way you like. 8n squared minus 12n plus 4 over 3n squared. And this right here is our lower sum. And if you remember our upper sum, that was 8n squared plus 12n plus 4. You see how similar they are. The only difference is that here we've got a minus 12n and here we've got a plus 12n. But these are formulas that will give us approximations for the area under that curve. This will give us an under approximation. This will give us an over approximation for a set number of rectangles, n being the number of rectangles.